The next step in our study of geometry after looking at the axioms of incidence geometry is to define those objects that we're going to be looking at more specifically. So today we're going to be looking at a lot of definitions. We're going to be defining the objects that we're going to be studying through the rest of the course and establishing, well, only their most basic properties here. We're going to have a whole lot more to talk about later. So today we're going to define distance, what it means for a point to be between two other points. We're going to define segments, angles, and triangles, all of our most basic elements of geometry, at least plane geometry. So we're going to go in order here. So we'll start with distance. So definition 9 tells us what a distance or a metric on a geometry is. So we want to say let G be a geometry. So that's a set of points, a set of lines, and a set of planes. We want that to be a geometry. A distance D on G is a function D which goes from S cross S. So it's going to take 2 points as inputs and it's going to give a real number as an output. And it has to satisfy 3 axioms. So I'm going to call them axiom D1, D2, and D3 for distance. So axiom D1 says that for all P and Q in S, the distance between P and Q is greater than or equal to 0. Negative distances aren't going to mean anything for our geometry. Axiom D2 says that for all P and Q in S, the distance from P to Q is equal to 0 if and only if P equals Q. So the only way for the distance between P and Q to be 0 is if they are in fact the same point. And then axiom D3 says that it doesn't matter which order you measure the distance in, that the distance function is symmetric. So for all P and Q in S, the distance from P to Q is equal to the distance from Q to P. And as long as we've got a function that satisfies these 3 axioms, we have a distance function on our geometry. Now, we're actually going to want something more than this. We're going to want to introduce another axiom, although we need a little bit of terminology first. And the reason why these 3 axioms themselves aren't good enough is that they allow us to define some really rather silly distances. So this allows for a distance function that goes from S cross S to R, given by the distance from P to Q is equal to 0 if P equals Q, and 1 if P does not equal Q. So this is a distance on a geometry which says that the distance between any 2 points is 1 if there are 2 different points. This distance D that we have here as an example satisfies axioms D1 through D3 pretty trivially in each case. But it really doesn't encompass what most of us intuitively think of as geometry, as what distance when looking at shapes and figures and things should mean. So this is really not very good. So we're going to want to introduce another axiom which tells us that we don't have this sort of weird geometry where everything is exactly as far away from everything else. But one piece of notation before we do that. So we usually write PQ instead of dpq. So notice that this PQ notation here has no decoration on it. It's just the point, the label for the point P, the label for the point Q written together. That's always going to indicate the distance between the 2 points that we're looking at. In particular, PQ is a number. So what we want in order to disallow the silly distances like we just had there is something called a coordinate system. So we'll take another definition. We'll let L be a line in our geometry. In a geometry S, L, P, D, where D is a distance function. A coordinate system for L is a function f that goes from L to R, the real numbers, satisfying 2 conditions. The first is that this function has to measure the distances between points. So the first thing is that we want for any P and Q in L, the distance from P to Q is equal to the absolute value of the difference between the images of those points under this function L, otherwise known as the coordinates of those points. So we'll often refer to this number f of p as the coordinate of p under f when we want to specify the coordinate system that we're looking at. And similarly, f of q would be the coordinate of q under f. The second condition, and we'll look at exactly how this works in a second, is that f has to be a bijection, meaning it has to be 1-to-1 and it has to be onto. So let's see how this works. If I take a line here, this line is a collection of points in my geometry. And what a coordinate system for L does is it takes every point on the line and maps it to some number in the real numbers in a very special way. So we might have that this point maps to 0, this point maps to 2, this point maps to 3, and -1 and -4, say. And so if I label these points here, P, Q, R, T, U, then what the existence of a coordinate system F here tells us is that, for example, the distance from P to R is equal to the absolute value of f of p minus f of r. Now, f of p we see is -4, and f of r is 0. So we get the absolute value of -4 minus 0, which is 4. So we see that the distance between p and r is 4. And we can do the same thing with the others. If I want the distance from q to u, well, I notice that the coordinate of q is -1, the coordinate of u is 3, and the difference between those things, the absolute value of the difference between them, is also 4. The distance from r to t is equal to 2, because that's the absolute value of the difference of their coordinates, and so on and so forth. So the function f assigns coordinates to each point on L in such a way that you can calculate the distance between any 2 points by looking at the absolute value of the difference of their coordinates. So that's what part 1 of the definition tells us. Part 2 says that F is a bijection, and this is really rather huge. And it does mean that lines with coordinate systems have a lot of properties that arbitrary lines back in instance geometry did not have. The biggest one is probably the fact that any line with a coordinate system has to have infinitely many points. In fact, uncountably many points. And this is because the real numbers have uncountably many, infinitely many points. And since F is a bijection, that means that the set L and the set of real numbers have to have the same cardinality. They have to have the same number of things inside them. So since R is infinite, L also has to be infinite. So any line that has a coordinate system has infinitely many points on it, which means that we aren't going to be dealing with just like the 2-element lines that we saw in instance geometry. We're actually going to be dealing with lots of lines here. And there are other things that it means. So for instance, this means, since F is a surjection, this means that given any point, or any number rather, any real number, there is some point on the line L that has that coordinate. What we're going to be proving in later talks is that this is going to guarantee us that we can always construct segments of whatever length we want. And any line is basically infinite in length because we can always construct a segment contained in that line which is as long as we want. So a coordinate system on a line means, in some sense, that line is sort of a copy of the real numbers placed inside our geometry. And we can measure distance using the coordinates that that coordinate system gives us. Now, this is very powerful when a line has a coordinate system for L. Our next axiom is possibly the most important axiom that we have had in terms of restricting what kinds of geometries we want to look at. So Axiom D4 is something that we're going to assume for all of our geometries. And Axiom D4 says that every line has a coordinate system. So in our geometries, all of our lines are going to have coordinate systems. This means in particular that all of our lines are going to have infinitely many points. We're now no longer looking at small geometries like we were looking at before. All of our geometries have infinitely many points because they all have at least a few lines in them. And in fact, this axiom right here is going to guarantee that our geometries have infinitely many lines and infinitely many planes. So the Axiom D4 is really important, and it's so important that it has a name. This is known as the Ruler Postulate. The idea behind this name is that Axiom D4 says that you can place a ruler, that is a copy of the real numbers, up against any line in your geometry. And this gives us a lot of structure to work with and a lot of facts that we can show. In particular, we will often use the following theorem, Theorem 11, which says that not only does every line have a coordinate system, every line has lots of coordinate systems, and we can always find a coordinate system that does what we want, that does what we want in a certain way. Given a line L and 2 points, A and B, belonging to L, there exists a coordinate system F for L such that f of A equals 0 and f of B is greater than 0. This theorem is known as the Ruler Placement theorem. And it says that if I have a line over here, and I've got some point A that I care about and some point B that I care about, then I can always find a way to set up a coordinate system for this line so that A has coordinate 0 and B has some coordinate, but whatever coordinate it has is positive. So the ruler placement theorem is quite useful for a lot of arguments that we're going to be making here coming up. So let's look at the proof of this. How would we prove that we can always come up with a coordinate system F that does this specifically? Well, the only thing that we know to begin with is that the line has some coordinate system. So let's let G be a coordinate system for L. And why can we do that? Why can we let G be a coordinate system for L? This is by Axiom D4, or you could say by the Ruler Postulate. That's perfectly fine. Now, this G might already be what we want, but probably not. So now, let little a be equal to G of A, the coordinate G of A. Now, define a function h from L to R by h of P equals G of P minus A for all P in L. So what we're doing here is we're defining a new function. So this new h, first of all, we're going to claim that it's a coordinate system, but we also have essentially shifted it by subtracting this little a from the coordinates of the points under G. What we're basically doing is we're shifting the ruler along the line that we're looking at. So now H is a coordinate system for L. Now this takes some justification, but this is an exercise. This is part of your homework. So you need to prove that H is a bijection and that it satisfies the condition where if P and Q are two elements of your line, then the distance from P to Q is the absolute value of H of P minus H of Q. And you're going to get at that by using the definition of H in terms of G and using the fact that G is a coordinate system. So it satisfies the conditions that you want. So H is a coordinate system for L, and we have that H of A is equal to G of A minus little a, but G of A is exactly equal to little a. That's how we defined little a to begin with, and so their difference is 0. So what we've come up with now is a coordinate system H, which has the property that when you evaluate that A, you get 0. If H of B is greater than 0, then we set f equal to h, and we're done. If it happened to be the case that h already had the property that the coordinate of b under h was positive, then h is the coordinate system we want in the theorem, and we're done. However, that might not be the case. So, if h of b is less than 0, then we need to do something else. Again, we can think about this fairly intuitively. We had a coordinate system, a ruler placed against the line of g, and then we shifted it back and forth until the 0 of that line, the 0 coordinate, lay on A. Now, if the coordinate of b is negative, that means that b is lying over here on the negative side of our ruler. So the thing to do to replace that is to flip the ruler. We're now going to take a coordinate system which is essentially flipped around 0 to give us a new one. So if h of b is less than 0, let's let f from L to R be given by f of p is equal to negative h of p for all p and L. Now, notice that f of b, it will be equal to negative h of b, but since h of b was negative to begin with, that's going to be positive. So the only thing that remains is to prove that f is a coordinate system. Now this will, I'll go through in general, and actually the process that we use here will be similar to the process you need to use on the first step to show that h was a coordinate system to begin with. So let's show that f is a coordinate system for L. So let's let P and Q belong to L. And what we have is we have f of, we want to look at f of P minus f of Q, and we want to show that this is equal to the distance from P to Q. Now, f of P we know is minus h of P, and f of Q we know is minus h of Q. And that means that we can rearrange this to get positive h of Q minus h of P, which equals QP, and that's because h is a coordinate system. And h of Q minus h of P is equal to the distance from Q to P, is equal to QP. That's since h is a coordinate system. And QP is equal to PQ by Axiom D4, that it doesn't matter which order we measure the distance in, we get the same result. So this means that the absolute value of f of P minus f of Q is equal to PQ. So that's step 1 of the process. So now we need to show that f is a bijection. Now we can prove this directly, and let's go ahead and do that, but then I'll also talk about how there's a potentially more clever way of doing it that just requires a slightly different perspective on things. So now let's prove f is bijective. Now, to prove that f is bijective means we have to prove that it's injective and it's surjective. So, for injective, or one-to-one, we start the following way. Let's suppose that f of P equals f of Q. And if f is injective, or to prove f is injective, we need to show that this implies that P is equal to Q. That if two inputs have the same output, well, then the inputs had to be the same to begin with. So suppose f of p equals f of q. This means that negative h of p equals negative h of q. So h of p equals h of q. But since h is injective, this means that p equals q. So therefore, we started with the assumption that f of p equals f of q. Our conclusion was that therefore p has to equal q, which means that f is injective. All right, what about surjectivity? For this, we need to show that every element of the target of the real numbers is hit by some point in L under F, that we can always find some element of the real numbers, or rather, for any element of the real numbers, we can always find a point that has that coordinate. So we want to say, let's let x be in R. Since H is surjective, there exists some P in L such that H of P equals negative X. So we don't want to find a point that H sends to X. We want to find a point that H sends to negative X so that we can get the following. F of P, which equals negative H of P, is going to equal negative X, which equals X. So we started with any element of the real numbers, and we found a point in the line that has X as its output when it goes into the function f, and therefore f is surjective. So this means that f is a bijection, and so a coordinate system. So that's how this proof goes. We can finish off our proof with a little box. Let me talk briefly about how we might do this last step of proving that f is bijective in a slightly more sophisticated way. So let's look at an alternative approach to showing f is a bijection. And there are at least a couple of different ways of doing this. One of them would be the following. So we have that, let's let sigma from the real numbers to the real numbers be given by sigma of x equals negative x. So sigma is just the function that multiplies by negative 1. Now, sigma is a bijection since it has an inverse, namely itself. So notice that if I take sigma of x, that's going to be sigma of negative x, which is just going to be x back. So that means that sigma as a function has an inverse, and any inverse is a bijection. So sigma is a bijection, Therefore, F, which is sigma composed with H, is a bijection, since sigma and H are bijections. And we know that the composition of two bijections is a bijection. So this would be one way of approaching things, using slightly more sophisticated machinery and knowing that any composition of bijections is a bijection. Another way of doing this would just be to show that F itself has an inverse. If you can construct an inverse to a function, that means that function had to be a bijection to begin with, because only bijections have inverses. So I'll make capital F go from the real numbers to L, be given by capital F of X is equal to H inverse of negative X. Now I know H inverse exists because, again, I know that H is a bijection. That was the hypothesis, that H is, or that was proved in a previous part of the theorem, that H is a coordinate system, hence is a bijection. Now, we have that for any P in L, we have that capital F of little f of P is equal to capital F of minus little h of X, which is, I'm sorry, F of negative H of P. Now we know that by definition, capital F of X is equal to H inverse of negative the stuff inside. But of course those negatives cancel, we just get H inverse of H of P, which is just P, because H inverse is the inverse of H. So that shows that if we compose capital F and little f in one direction, we just get, and apply to P, we just get P back. And then for any X in L, X in R rather, if we go the other way, if we take little f of capital F of X, that's going to be little f of H inverse of negative X. Now F of something is equal to negative H of that thing. Now H of H inverse of X is, negative X rather, is just negative X, which just gives X back. So this means that capital F is equal to the inverse of F. Little f and capital F are inverses of each other, and hence F is a bijection. My point is that there are several ways of proving that a function is a bijection. You don't just have to prove injectivity and surjectivity directly, and some of them are somewhat more efficient ways of doing it, but they also might be a little bit harder to wrap your head around at first. All right, so the ruler placement theorem is actually quite useful for us, and we're going to use it in a lot of proofs that we do. The next step is to talk about betweenness. What does it mean for a point to be between two other points? And this is going to be another very important concept that we work with a lot. So let's look at betweenness. So let's just start with the definition. So definition 12, let's let A, B, and C be 3 collinear points. We say that B is between A and C, and we write the notation A dash B dash C, or just ABC, if the following is true. If the distance from A to C is equal to the distance from A to B plus the distance from B to C. We can look at a simple example to see that this matches what our intuition says should be meant by something being between two others. So if I look at this line with A, B, and C on it, I can look at the distance from A to C, and I can also look at the distance from A to B and the distance from B to C. And we can observe that in this setup, at least again following our normal intuition, the distance from A to C should be the sum of the distances from A to B and the distance from B to C. And so when that happens, when intuitively B is between A and C, we have this property involving sums of differences. So we're going to use that property of sums of distances to define what we mean by betweenness. Now, when we think about things in terms of a coordinate system and the ruler placement theorems and such, we have alternative descriptions of betweenness. And the next lemma is going to be extremely convenient for us. It gives us 4 different ways to understand what it means for a point to be between two other points. So lemma 13 says, let A, B, and C be collinear, be 3 collinear points. We want them all to be different. And then the following are equivalent, TFAE. And what that means is that of the 4 things I'm about to write down, if you know any one of them, that means that all the rest of them are true. So one of the following is just B is between A and C. So if B is between A and C, that's equivalent to saying that for all coordinate systems, F for the line AB, which also includes C, because they're collinear, either F of A is less than F of B is less than F of C, or F of A is greater than F of B, and that's greater than F of C. So part 2 here is saying that if I have some coordinate system, if I have any coordinate system really, on the line, and I look at the coordinates of A, B, and C, then if B is between A and C, if the points are, then the coordinate of B is going to lie between the coordinates of the other 2. So really betweenness on the level of the line, points on the line, is equivalent to betweenness on the level of the coordinates of points on that line. So to check for betweenness, we can look at the points or we can look at their coordinates. Then 3 and 4 say that there exists a coordinate system for the line AB with F of A less than F of B less than F of C. So part 3 says that if there exists some coordinate system where the coordinate of B lies between A and the coordinates of A and C, that means that B itself lies between A and C. And also this means that if we know ahead of time that B is between A and C, then we can always find some coordinate system where their coordinates are increasing as we move from A to B to C. Number 4 is very much the just the inverse. There exists a coordinate system for AB, for the line AB, with f of A greater than f of B greater than f of C. So Lemma 13 is really helpful because it lets us translate problems involving points on a line and a definition of betweenness that involves sums of distances into just looking at betweenness of numbers, which we understand well. So we're not going to go through the proof of this. So right here, you can find it in the notes. It's somewhat technical, but a lot of it is based on the ideas from the proof of the ruler placement theorem. So for instance, to prove that 3 is equivalent to 4, if I know that I've got some coordinate system where the coordinates are increasing, I can just take the negative of that coordinate system, and I'll get a coordinate system where the coordinates of the 3 points are decreasing. So that's how we can show that, for instance, 3 and 4 are equivalent, and we can do similar things for all the rest. So to see why Lemma 13 is so useful, let's look at another theorem which talks about some of the most important properties of betweenness. Theorem 14. Theorem 14, I want to say let A, B, C be 3 collinear points. And then we have a few different pieces here, which will label B1 through B4 because they are sort of our most basic betweenness results that we'll want to reference reasonably often. So first of all, if B is between A and C, then B is between C and A. So in other words, the betweenness relationship is symmetric in the outer points. B2 says that given any 3 points on a line, exactly one of A, B, and C is between the other 2. We can't have that B is between A and C, but also that A is between B and C. That doesn't work. Exactly one is between the other 2. B3, any 4 points on a line may be labeled A, B, C, D, such that we have the betweenness relationships A to B to C to D. Now this notation here is new one, and this just means that the following betweenness relationships hold. If we take any one of these points out of this notation, then the betweenness relation we get out of that holds. So this notation here means that that B is between A and C, and B is between A and D, and C is between A and D, and C is between B and D. So this notation with the 4 points just means that if I remove any one of them, I get a normal betweenness relationship, and all of those hold. All 4 of those hold. B4 says that if A and B are 2 points, then there exist C and D such that A, C, B, and A, B, D. This is a very important point right here. And we're going to use it quite a lot, and we're not going to make a lot of fanfare about it, but it really is vital to what we're going to be doing in geometry. This is saying that given any 2 points, there's some other point between them. That's what the first part of this says. And it also says that given any 2 points on a line, well, any 2 points do lie on a line, I can, as I said, I can always find something between them, but it means I can always find something on the other side of B from A. Of course, I could do that in the other direction too, and I could say, by just switching the role of A and B, I can, B4 here says that there also exists some point over here on the other side of A from B. So B4 gives us a way of constructing points basically in any position that we want, which is quite useful for us. All right, let's see how we go through a couple of the proofs here. Now, for B2, B3, and B4, we're going to use the lemma 13 characterization. We're going to use coordinate systems to make them work. B1 can actually be done using the definition, and we don't want to forget the definition, even though we have the coordinate system way of thinking about things. So for B1, let's suppose that A, B, C, which means that AC is equal to AB plus BC. Now, if we change the order of all of these distance terms here, that's not going to change the actual distance. So that means that CA, which is equal to AC, is going to be equal to BA plus CB. Because CA equals AC, BA equals AB, and CB equals BC. And furthermore, we can rewrite the right-hand side of this equation just by exchanging the order of the terms, because of course addition doesn't care about what order you do things in. But CA equals CB plus AB is exactly the definition of betweenness. This is exactly what we would use to conclude that B lies between C and A. So B1 is a very quick way of doing things using the original definition. Though, again, we want to use the coordinate system approach for the others. So let's look at those. So for B2, we're trying to show that exactly one of A, B, and C is between the other two. So let's just let F be a coordinate system for the line AB. Of the numbers F of A, F of B, and F of C, exactly one is between the other two. Because if we have any three numbers, we know that One of them is going to be the minimum, one of them is going to be the maximum, and the one that's left is going to be in between the other two. Exactly, one is between the other two, and so by lemma 13, the corresponding point is between the other 2 points. B3 does something similar. So we can let, I don't want to label them A, B, C, D because B3 says that we can relabel them that way to get the betweenness relation we want. So let's let P, Q, R, S be collinear points, be 4 collinear points. And let's let F be a coordinate system for the line PQ. So now we've got 4 numbers. Now we've got 4 numbers, F of P, F of Q, F of R, and F of S. We can look at the coordinates of these 4 points, and we can arrange them in a certain order. We can arrange them from smallest to greatest. Now we don't currently know which of P, Q, R, and S are going to be the largest or the smallest, but we can relabel them, which is sort of the point of B3. So let's let A, B, C, D be 4 points, or be the 4 points P, Q, R, S, but such that A has the least coordinate of the 4 of them, B has the second least coordinate, C has the third least coordinate, and D has the highest coordinate. So now A, B, C, D is a relabeling of P, Q, R, S, but we have that we have the relationship A to B to C to D. And then finally B4 says let A and B be 2 points, and we want to find a point that's between A and B, and we want to find some point D such that B is between A and D. So here we're going to use our ruler placement theorem for the first time. It's not strictly necessary, but it makes the theorem a whole lot simpler to write down. So let F be a coordinate system for the line AB such that F of A equals 0 and F of B is positive. So now we want to find points C and D that match what we want. So we know that we've got F of A, which is 0 right here, and then we've got F of B, which is positive up here, and we want to find some number in between them. Or rather, we want to find some point in between A and C. So we can, for instance, do the following. Whatever the coordinate of B is, F of B, it's a positive number, which means that if we take F of B divided by 2, for instance, that's going to be less than F of B. But it's also going to be greater than 0. So 0, or rather, let me start this way, F of A is equal to 0, and that's going to be less than F of B over 2, which is going to be less than F of B. So let C equal F inverse of f of b over 2. In other words, let C be the point on the line which has a coordinate of f of b over 2. Now, of course, we didn't need to do this specifically. There are lots of points in between A and B we could have chosen, but B4 just says there exists some point. So as long as we come up with some point, we're fine. So now, by lemma 13, we'll have that C lies between A and B. So the beauty of the Ruler postulate is that if you find any number that satisfies the betweenness relationships that you want, that always comes back down to some point on the line that satisfies the betweenness conditions that you want, because coordinate systems are bijections. And we can do the same thing over here with D. We can just take anything bigger than f of b. So for instance, f of b plus 1 is a perfectly good thing to take. So we could let D be f inverse of f of b plus 1, and then we'd have that A to B to D. So trying to prove B2, B3, and B4 without using lemma 13 would be tedious. Trying to prove it without having the Ruler postulate at all would be impossible. In fact, there's at least one other major point of view or approach to geometry which doesn't assume that we have the real numbers, which doesn't assume that we know about the construction of the real numbers or its properties or anything else, and just works with points and lines and planes and never makes reference to anything outside of that. And that's called synthetic geometry. And in synthetic geometry, these these statements B1, B2, B3, B4 that we have to be taken as axioms. They have to assume that B1, B2, B3, and B4 hold and go from there. We are working with the real numbers and the Ruler postulate, which gives us a lot more power to work with, but it does have the I don't know if you want to call it the downside, but it is the case that we're relying on things we already know about the real numbers. So this isn't a pure geometry approach anymore in some sense. We're using stuff that we know from analysis or calculus to talk about how the real numbers behave. Nevertheless, this is a very good approach to geometry, and it's much easier to actually get to the point where we're proving interesting things using our approach than the synthetic approach. So now that we know about betweenness, that's going to be key to defining segments, rays, angles, and triangles. So that's the next thing that we want to do. We're going to define these. We're not going to prove too many things about it except as refers to their description, because the rest of the course pretty much is going to be about what can we prove about segments, rays, angles, and triangles. So let me just call this figures, geometric figures. So let's look at our definition 15, and this is going to be quite an important definition that you'll want to make sure that you have completely correct when you go to work problems. So let's let SLPD be a geometry, and A, B, and C, 3 non-collinear points. So, first one, the segment AB with a bar over it is a set. It's a set of points, and it's the set of all points x in the line AB such that x is between A and B. And then it also includes the points A and B themselves. We can draw a figure over here to keep track of what we're doing. So what we have from previous geometry knowledge is that the segment between A and B should look basically like this blue part here. And so it includes two types of points. It includes the endpoints, A and B, and it also includes all the points that are in between A and B, that lie between A and B. So that's the segment AB. Now, if we want the ray, and this notation is AB with a single arrow over, is, first of all, it contains the segment AB, but it also includes more. So the ray is going to start at A and go through B and continue on. So in particular, notice that it includes all the points in the segment from A to B, but it also includes extra points out here beyond B. So the ray AB is going to consist of the segment AB and all of the elements of the line AB such that B is between A and X. So the ray AB is the point A, the point B, everything in between them, and then everything such that, all the points X such that B is between A and X. And that's how we would define that ray. The angle, angle BAC, is the ray AB union with the ray AC. So in geometry, an angle is just a union of two rays. It's just a set of points. So it's just the edges. It doesn't include the interior of it. We'll be talking about the interior of angles at a later point, but the angle, angle BAC, just looks like this. Notice that for the ray and the angle, the order that we write things down in matters. The ray AB is different than the ray BA. The ray BA would go the other direction here. And then similarly, with the angle BAC, the middle point here is the vertex of the angle. It's the point where the angle makes a corner. So the order that these are written down in does matter up to a certain point, but that's what the next theorem is going to tell us. That is how much does the order of these things matter. And then finally, the triangle ABC is the union of three segments. It's the union of the segment AB, the segment BC, and the segment AC. So we'll do that in yellow over here. So that'd be the segment AB, the segment BC, and the segment AC. And again, the triangle is just the union of those segments. It doesn't include the inside of the triangle. It's just the point on those segments. And we refer to the A, B, and C as the vertices of the triangle. One thing that's quite useful is that we can describe segments and rays in terms of coordinate systems. So if F is a coordinate system for the line AB, and let's say we have that F of A is less than F of B. We can always find a coordinate system that does this by the Ruler placement theorem. Then the segment AB is equal to the set of all points x in the line AB such that f of x lies between f of A and f of B. But now we can use the weak inequalities in order to capture the two endpoints within this single set construction. Because if x is equal to A, then f of x would be equal to f of A, and so it would still satisfy this condition. We can do a similar thing with rays. So if f is a coordinate system for AB with f of A equals 0 and f of B greater than or equal to 0, or strictly greater than 0, then the ray AB can actually be described as the set of all points on the line where the coordinate of the point is just greater than or equal to 0. So the ray can actually be described very easily. If we take A and we take B, then the ray is given like this. And if we look at a coordinate system where A has coordinate 0, B has coordinate greater than 0, then the ray just consists of all the points on the line that have coordinates bigger than 0. So starting at A and going basically in the direction of B. So this can be a useful fact when working with segments and rays. You can always introduce a coordinate system which characterizes the segments and the rays using the real numbers fairly efficiently. Now, when we're working proofs and such, we have to be careful when writing things down. Sometimes we will want to use abbreviated notation. So, given this figure, there are lots of different angles and that we could talk about here. We may write angle, say PQR, as simply angle Q, just referring to the vertex, if no confusion is possible. So, for instance, in the figure above, angle A works. We can just refer to angle A, and angle A refers to the angle BAC. So this angle right up here, and that's And that's fine. We can do that because there's only one angle that could be described using the points that we have at A, using the points and segments that we've noted at A. However, if we tried to write down something like angle B, this is ambiguous. Because if I look at angle B, I could ask, am I talking about this angle here? Am I talking about angle ABC? Or am I looking at this angle here, angle ABD? It's not clear based on the figure that I've drawn. So in that case, if we want to refer to an angle with a vertex at B, we must use angle ABC or angle ABD to remove the ambiguity there. Similarly, C is ambiguous. Angle C is ambiguous. And then angle D is also ambiguous because there's no defined angles at D. By defined here, I mean ones that we've either sketched out in our diagram or mentioned in our proof. Something like this. So it's unclear what is meant by the angle at D. Let me point out here that in contrast with what we see in like trigonometry and such, this is not considered an angle. We do not consider straight angles to be angles. Remember back in the definition from the last page, in order for angle BAC to even be defined, we required that AB and C be non-collinear. In particular, this means that all of the angles that we're looking at are going to be, none of them are going to be straight. When we get into measuring them, all of our angles are going to be strictly between 0 and 180 degrees. Not equal to 0 degrees, not equal to 180. So for us, a straight angle is not an angle, and therefore this figure has no angles at D. All right, so last thing that we're going to do is we're going to look at Theorem 16, which tells us how we can write a single figure, a segment, ray, etc. in different ways without actually changing what it is. For any points A, B, C, D, E, F, where the objects below are defined, so part 1, the segment AB is the same as the segment BA, and that comes from the fact that betweenness doesn't care about the order of the two things on either side. Part 2, if D belongs to the ray AB but is not the endpoint of the ray itself, then the ray AD equals the ray AB. So the picture here is that I've got a line and I've got a point A here and I've got a point B here, and I've got some ray that I've constructed. And now if I pick any other point on this ray other than A and construct the ray through that point, it's going to be exactly the same set. So the point B really doesn't matter when defining the ray. All that matters is that you choose some point that's on that line on the correct side of A. Similarly, if D belongs to the ray AB but is not A, and E belongs to the ray AC, but again is not A, then the angle BAC equals the angle DAE. So the picture here is that if I've got an angle and I've got points A, B, and C, so here I've got angle BAC, and then I pick any other point on the ray AB, and I pick any other point on the ray AC, then that's going to give me the same angle. Now, we haven't started talking about congruence yet. When we say that that these segments or rays are equal, we mean equal as sets. They contain exactly the same points. They lie right on top of each other. So let me let's go on to part 4. So if the segment AB is equal to the segment CD, then the points AB are equal to the points CD. This is basically saying that a segment is defined by its endpoints. That it's not possible to have some segment here where I've got A and B. It's not possible to somehow weirdly have a C here and a D over here and have the segment AB equal the segment CD, unless C and D were the endpoints A and B to begin with. Now, it could be that A equals D and B equals C, or vice versa, but the point is that the endpoints of a segment define that segment. Similarly, if I needed an if in front of here, if triangle ABC equals triangle DEF, if I've got two different ways of describing a triangle, then the vertices ABC, the set of vertices, is equal to the set of vertices DEF. So this means that a triangle is entirely determined by its vertices. And so again, this is saying that if I've got some triangle, that it's not possible to weirdly choose a D, E, and an F that are different than A, B, C in order to get the same triangle. Believe it or not, this item 5 here is quite a challenge to prove. It takes quite a bit of work and some fairly sophisticated arguments. So if you want a good challenge, go ahead and work on that one. It takes some thought. It takes some work. So there we have the definitions of the objects that we're going to be spending a lot of time moving forward working on: segments, rays, angles, triangles. And here we've got their basic properties. We know how to describe them. And so next time we'll be able to start working on proving things about them in earnest.